Okay, so well known again. I have checked your homework and you all did well. Very good job. So today we will continue learning about the model. So I would like to review quickly what we have learned last week. Okay, okay. So last week we start from the data. Like we have the set of the data of y and x, which may be price and quantity. So what should we do with those kind of data using the model? So okay, let's first we try to plot the data together. Okay, whether two variables have a relationship between each other, and then we plot, and then oh, they are somewhat have a relationship to each other. Then we try to make a line which draw through the data, and this line is called econometric, which we use the technique called OLS, ordinary least square. Okay, ordinary least square. With this technique, they try to minimize sigma error hat square. And then using the Gauss-Markov rule, Gauss-Markov theorem, Gauss-Markov said that first, if your model is correct, then average error, which we can write down as expected, average error is 0. Then the variance error is constant. Then covariant error is 0. And then X is not random. Is not random. And lastly, error is normal distribution as average 0 as the constant variance. So from the Gauss-Markov theorem, they said if first five rules first five rules are true, okay, OLS will be the best linear unbiased estimator, the best, okay. Why the best? Because they can provide a minimum sigma error hat square. That's why they have mean variance. Okay, what is mean variance? They mean this one, which this one we use for calculate. This one we use for calculate variance of this one and standard error of this one. All of them we have the minimum value, which means it's the best model in the world. They claim only if this one, this one, this one, this one, this one are all true. Okay, we later learn it. But okay, let's back from the data. After we get the data y and x, we try to make the line. So two data together, we can obtain each beta, right? We calculate it together in the homework as well. And then we can calculate its standard error. And that's what we learned so far. So today we will use two things together, beta and standard error, to see whether can we trust or believe that these numbers are correct. Okay, so after we can calculate each beta, we calculate standard error. Today, we will use two numbers together to test whether can we believe in those numbers we calculate. Okay, so we will do two things. Okay, first we call confidence interval. Okay, confidence interval, and we will do hypothesis testing. And then we will try to use a program a bit and we'll finish the class today. Okay, this is what we will learn together in this class. Okay, this is our data from previous chapter. Okay, the same story. We have y, we have x. We plot the data and we make this line, the orange line, and then we can calculate each beta and each standard error. So after we obtain all the information we need, what shall we do further? Okay, first, this is how we write an equation. Okay, when you obtain the data and obtain the beta and standard error, and you have to write the report or you have to read other report, they will write down their equation similar to this type. Okay, y hat equal beta 1 hat plus beta 2 hat x. So they view what they found in the equation. And then on the second line, they use standard error under their beta in the bracket. Okay, this is the style that you should write down in the future. Standard error in the bracket under is beta. So what will we do next? First, we will make a confidence interval. This means range of values gives a sense of what the parameter value might be. The second one we call hypothesis testing. It means is the number correct? Uh, sorry, uh, my bad. Oh, end of chapter now. Accident is accident. Okay, so hypothesis testing is mean can we know that the number is correct statistically. So we use statistic to prove those number whether can we believe. For example, this number we got 1.93, which means if x increase by 1, y will increase 1.93. But is it correct? Can we use this number? Okay, so to answer those two questions, you have to do hypothesis testing, which is the main content of this chapter. Okay, but let's start from how to construct a confidence interval. There are two ways of estimate. First, we have done last week together. We call a point estimate, which means we got one number. Okay, a point estimate is a statistic compute from sample information, which is used to estimate the population parameter. Okay, we don't know. This is mean we if I don't put hat on it, it means the true value. We don't know the true value, so we estimate beta hat. Okay, we can estimate it, but for the confidence interval estimate is the range of values construct from sample. So the population parameter is likely to occur within range at the specified probability. The specified probability is called level of confidence. Okay, so a point estimate is mean we have one value to represent the estimate beta. But if we try to make interval, it means we give range of value. So we would say that we have confidence that beta is between some value. See the example? Okay, so from previous data, we got point estimation equal 1.93, but we don't know that this number is correct or incorrect. Okay, then we try to make an answer to be interval. Okay, then we try to answer that, okay, after we estimate slope to be 1.93, what about the two values? So the two value maybe range between some number and some confidence interval. In economics or maybe in statistics, they have three main confidence level. Okay, so we would say we have a 98% confidence interval estimate for beta 2. Okay, typically we use three value 90% confidence, 95% confident, which is widely used by statisticians and economists. Okay, and also 99%. Okay, we have three confidence level. And then to construct confidence interval, we use this formula. So the real beta equal what we forecast plus and minus critical t multiplied by standard error. Okay, for previous chapter, we have data and then we estimate beta already. We estimate standard error already. So we have this data, we have this data. What is it? So this is called critical T. Yes, critical T. So then to construct confidence interval, we have to know how to find it. T distribution. Let's read this example. Example, if we have 95% confidence interval, it means an interval that has probability of 0.95 or 95% confidence of containing the parameter beta 2 when the procedure we use is applied to many samples of data from the same population. If we done it many times, then 95% of our interval estimates construct using this procedure will contain the two parameters. Okay, you may confuse now, but I would like to say that, okay, we got beta from previous chapter, we got standard error for previous chapter, so we have to know how to find T stat. So this is T distribution. So T distribution, normally there is a normal distribution. Okay, so the area under normal distribution is 100%. And then I told you already, we have T level of confidence. So we have 90% confidence, we have 95% confidence, and we have 99% confidence. And then we have another vocabulary that widely used by statisticians and economists we call significant level. Let's see the relationship between confidence and significant level. So if we say we have 90% confidence, it means we use 10% significant level, or we can say alpha. This is alpha. Oh, I wrote it wrong. Alpha. So this is alpha. So the significant level literally means how many error we can accept. Accept. For example, if you have confidence only 90%, what does the 10% left? Oh, it means the error that I can accept because I have confidence only 90%. Again, if I use 95% confidence, it means my confidence is just 95%. What about 5% left? Oh, is an error that I can accept. So I use 5% significant level. Okay, and you see the relationship between two values. Again, if I have 99% confidence, which means 1% left is an error that I can accept. I can say, oh, is 1% significant level, or I can say alpha equal 0.01, which literally means 1% as well. Moreover, they have error both on positive and the negative. For example, if I say that beta must equal 2, it can be, oh sorry, if I would like to say that beta is not equal to, it can be that, okay, if beta is greater than 2, okay. If beta less than 2, okay. Just not equal to, that's okay. So we have both positive way and the negative way. We call this type of testing to tell. Alternatively, if I would like to test whether beta is greater than 2 or not, it means only way that make this sentence correct, only beta greater than 2, right? So this type we call one tail, one tail. And then back to what we would like to do. We would like to do confident interval. Okay, the confident interval, they have both positive and negative. So confident interval is to tell. Confident interval to tell. Okay, so slowly all the knowledge together, we can draw a normal distribution. For example, if I say I have 90% confidence, okay, this means if I draw normal distribution, this is 90% confident or 10% significant level. It means your confidence is 90% on the central. And then we can accept 10% error, right? Because we have confidence only 90%, which means we have to divide 5% on the right and 5% on the left. So 90% here on the central, and then we accept 5% error on the right. We accept 5% error on the left. Again, if I write down 95% confident or 5% significant level, if I draw the normal distribution, it means 95% on the center. And then, yes, correct. Very good. So we have to divide 5% both left and right. That's why if I would like to talk about T distribution, 90% confident, 10% significant level, it means T 0.95. Why? It means if you want this value, okay, you want to know this value, you have to open here 95, so T 0.95. Why? Because let's see next slide. Because mostly T table they provide the data of this area. So we would like to get the T data of this point. So we try to know which area we have to open. Let's do it together. For example, to find the critical T for confidence interval, this is a number of observation, the number of sample, okay? And then we have to open T n minus 2. So, yeah. So 95% confident. So if you still new to that, you may, 95% confident, 95% on the central, 2.5. Oh, it means we have to open this area T 0.975, and you have to minus 2, so n minus 2, 18. Altogether, we have to open T 0.975, 18. Then we look at the table. Oh, okay. T 0.975 is here. And degree of freedom. So the second number we call degree of freedom. Degree of freedom is 18. And then we dot 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 dot. We finally get the value we need is equal to 0.101. Good. Okay, next, n equal 15. Please find 99% confident. Okay, so 99% is mean 99% on the center. It means we allow 0.5% on both sides. So we have to open T 995. Too fast? If we draw it, because my drawing is so bad and it's difficult to read, right? Okay, one more time. I will make it bigger. Okay, so 99% confident, normal distribution, 99% here. So we have 1% left, which means we allow error 0.5% on the left, 0.5% on the right. And since G table they represent this value, so we have to open 995 is mean 0.5 plus 99%. So it's 99.5, 995. Okay. Uh-huh. So and 15. So 15 minus 2, 13. Yeah. So 0, 995, 13. So we got this number. So 3.012. Good. Then 90% confident. Okay. To do it slowly, 90% on the center, and we allow 5% on the left, 5% on the right, because total must be 100%. So 90 plus 5 is 95, is mean 0.95. So we have to open 0.95 minus 2, we get 498. And then you will confuse, Professor, hey, the table have only 50 and then infinity. So I would say that if n is large, for example, greater than 100, if n is large, greater than 100, you can use infinity. So this time 0.95 infinity, we get 1.645. So this is one of the example how to find t-value using the table. If you face this style of table, you have to know, okay, whether you do one tail, two tail, and how many level of confidence. But if you lucky enough and you find this type of table is easier to use, I will show you it's easier. For example, I would like to find, I hate this tab. How can I hide this one? Okay. For example, if you would like to make a 95% confidence interval with degree of freedom 15, what shall I do? If you have this type of table, it's easier you can go to, okay, you would like to do confidence interval 95%, and then 15. So you get the value 2.131. Okay, so if you use this table, it may be easier. Again, we would like to know 99% confidence with the degree of freedom 100. So we go to confidence level and then 99% and then 100. So we get, yes, very good. 2 point, oh, 2.626. I said 2, but I write 6. Just got my confusion. Okay, so you did it very well, and you now know how to use t-table. Okay, so what shall we do next? We would like to construct confidence interval. So let's do it together and see what will help you to construct and make a interval estimate. So we would like to construct a 98% confidence interval estimate for beta 2. So we use this formula, real beta equal what we forecast plus and minus critical value multiplied by its standard error. And then from the last example, we got all the value here. Okay, we have beta. Okay, this is how to read. This is the beta, the slope, and this is, what does it mean? What is the bracket? What does it mean? This means standard error. Okay, if you face equation like this and then make a bracket under the beta, you have to know it is standard error. And then we got n equal 5 and alpha. What does it mean? Alpha 0.05 is mean 5% significant level. What does it mean? 5% significant level is mean you accept 5% error or you have 95% confidence. Okay, and you relate all the number together. So first, this one, they would like to make a 95% confidence interval. So we know beta 2 already here, 1.93. We know standard error already here, 0.26. So we would like to know T. Okay, so we go and open T table. Okay, so 95% confident is mean, okay, 95% of the central. Okay, we have to open T 0.975 and 3, and then we go to the table, to 0.5 and the freedom 3, we got T.182. So we use T.182 here. And then we multiply 3.182 with 0.26, we got 0.83. So we got 1.93 plus and minus 0.83, which means you have to use 1.93 plus 0.83 and minus. Yes, good. Yes. And finally, if you calculate it, you will get 1.1 and 2.76, which mean this is a mistake of my whole point. You have to have equal sign as well. Mhm. So it means after we did a point estimate 1.93. Okay, listen. This is the most important. Okay, after we have the data, then we get point estimate. This number we got 1.93, and then someone will ask you, hey, can we trust this number? Can we trust the point estimate or not? We may say that, okay, 1.93 is correct or incorrect, I don't know. But we have 95% confidence that the real beta must be between 1.1 to 2.73. One more time. Okay, we did estimate together last week. We got 1.93. And then someone asks you, hey, do you believe this number? This is correct? You said, yes, I don't know it's correct or not, but we have 95% confidence that the real beta, because we don't have that, right? Okay, the estimate, correct, incorrect, we don't know, but the real beta must be between 1.1 to 2.76. So this is the meaning of confidence interval. Okay, so let's practice together. Okay, so after we compute 95%, we got the beta 1.1 and 2.76. First question, please compute confidence intervals at 90% and 99% level and discuss the results. Okay, so let's do 99% first. So the formula here, beta equal, beta had the same, right? So the same, plus and minus t multiplied by standard error, same, 5.841. Thank you. 5.841. I will change the color. 5.841. And then find me also the 90%. So the formula will be the same. Beta plus equal 1.93 again, plus and minus again. 1 point, again, 1 point. 2.353. Three. Okay, like this. Okay, thank you so much. Good job. Without any calculation, How about 99% compared with 95%? Is it wider or narrower? Do you get wider value or narrower value without calculation? Okay, I will write down again for the 95%, 95%, t value is 3.182, and the rest is the same, right? Because the formula is beta 1.93 plus minus. Okay, so beta has same standard error, the same, except the critical value. And the higher confidence, the higher t that you obtain. Okay, again, the higher confidence, the higher t stat you obtain from the table, which means when you calculate the beta plus and minus, which one? 90? Okay, 90 first. 1.31 to 2.34. And 2.34. Okay, and the uh-huh. 0, 1, 2, 3.45. Thank you so much for your hard work. And then what can we summarize of the level of confidence and the wider or the narrower of the answer? What can we conclude? Okay, so you can say that the higher confidence or confidence, sorry for my spelling, I don't make a mistake. A higher confidence, okay. The wider answer. Why? That's right. Okay. If we have less confidence, we get the very narrow answer, like just only 1.31 to 2.34, very narrow. But after yes, 95, wider answer. 99% wider, even wider answer. Why? Because if we have more confidence, it means we fear of mistake. We fear of error. So to prevent an error, we try to make a wider answer. This is what we get from this example. Okay, we try to prevent the error because we said we have more confidence. Okay, to prevent error. Second question. How about 95% confident interval, but you have a larger sample? For example, in 50. Mhm. So again, 95%, but n equal 50. Let me see. Maybe 52 is better, 52. Okay. Okay, I would like to say 95%. Yeah. So then the beta the same 1.93 plus and minus standard error we assume unchanged, so 0.26. So only piece that we have to find the new value in it. Yeah. So compare n equal 5, we got 3.182. How about if n equal 52, which means we have to find degree of freedom 50. So go to table 95% degree of freedom 50. We don't have 50 here. Okay, this one is better. So 95%, 50, 2.009. Thank you. 2.009. Without any calculation, what can we conclude? The relationship between the number of observation and confidence interval. Do not do calculation. Just see, do, we. Small. Yes. Thank you. Narrower. Narrower. Thank you. Yes, that's good. That's good. That's what the point. So the higher number of observation, the narrower answer. So what does this mean? It means if you collect more data, if you have more data, okay, for example, yes, if you have more data, like, okay, first you may have only few data, 100, 200, and then you collect more. Yes, the answer is more accurate, right? Because you get the narrow answer, which means your model is better. You can squeeze the answer to be narrower and narrower and narrower. But you can see key table again. Degree of freedom here for simple linear regression, we have to compute degree of freedom equal n minus 2. So degree of freedom is depends on n. So first, we have lower degree of freedom, which means lower the number of observation. And then we have more and more degree of freedom, higher degree of freedom, until let's see this number together before we take some rest. From 80 to 100 of 95% confidence, they change from 1.99 to 1.984. Very small, right? Change very small. Compare with, okay, maybe 1 to 2, 12 to 4. very large number of chain, right? But if you get the higher observation, so 80 to 100, change a little bit. Then 100 to 1000, 1.962, change very small fraction, very, very small. So can we summarize? The higher number of observation, the narrower answer, but until the number is large enough. If your number is large enough, even you collect more data, it will not improve your answer anymore because your number is large already. That's why sometimes the table provide you just some certain number and then they said infinity. It means the number is close. Okay, so I have a magic number that you maybe use it in the future and it is very useful. I told already that 95% confidence is more used is more used by econometricians. So it's good if you remember this number because it have a role in the future. So 95% confident. Oh, confident. I always use a crack. 95% confident with n is large enough and equal infinity. It's good to remember this value 1.96 here 1.96, so t equal 1.96 or around 2. Yes, this one is good to remember because we use this number frequently. Any test in the future, when we say 95% confident, we will see the two value around 2. And this will help us to not come to open the table again and again in the future. Okay, just 95% again, 1.96 on around 2. Do you want to break for a while or continue until finish? It's your choice. I'm okay on both. Do you want to take some rest or continue learning until the end and finish adding? Huh? เอาไงดี It's okay. Are you still fresh or you ate egg right now? If you ate egg right now, maybe take some rest. But if you, professor, it's okay. And it's not that hard. We can continue. Okay, so what choice? What is your choice? To Relax. Okay. Take some rest first. Take some rest. Take some rest. So maybe 15 minutes. Just break with water, and then we will study another topic. I think we can finish the class early today. Mhm. Okay, let's break for 15 minutes. So we will back on 14:50. Okay, so we, yes, we have done the first part of this chapter, confident interval, and the second part is similar. We call hypothesis testing. Okay, so a hypothesis testing is the statement about the value, okay, of population parameter or the true value. Okay, so hypothesis testing is procedure based on sample evidence and probability theory used to determine whether hypothesis is a reasonable statement and should not reject, or unreasonable and should be rejected. I think I provide the video here, so maybe let's see video first. Okay, 5 minutes of video, not so long. See the concept.
There are 4 steps in data-driven decision-making. First, you must formulate a hypothesis. Second, once you have formulated a hypothesis, you will have to find the right test for your hypothesis. Third, you execute the test. And fourth, you make a decision based on the result. Let's start from the beginning. What is a hypothesis? Though there are many ways to define it, the most intuitive I've seen is: a hypothesis is an idea that can be tested. This is not the formal definition, but it explains the point very well. So, if I tell you that apples in New York are expensive, this is an idea or a statement, but is not testable until I have something to compare it with. For instance, if I define expensive as any price higher than $1.75 per pound, then it immediately becomes a hypothesis. Alright, what's something that cannot be tested with a hypothesis? An example may be: would the USA do better or worse under a Clinton administration compared to a Trump administration? Statistically speaking, this is an idea, but there is no data to test it. Therefore, it cannot be a hypothesis of a statistical test. Actually, it is more likely to be a topic of another discipline. Conversely, in statistics, we may compare different US presidencies that have already been completed, such as the Obama administration and the Bush administration, as we have data on both. Alright, let's get out of politics and get into hypotheses. Here's a simple topic that can be tested. According to Glassdoor, the popular salary information website, the mean data scientist salary in the US is $113,000. So, we want to test if their estimate is correct. There are 2 hypotheses that are made: the null hypothesis, denoted H0, and the alternative hypothesis, denoted H1 or HA. The null hypothesis is the one to be tested, and the alternative is everything else. In our example, the null hypothesis would be: the mean data scientist salary is $113,000, while the alternative, the mean data scientist salary is not $113,000. Now, you would want to check if 113,000 is close enough to the true mean predicted by our sample. In case it is, you would accept the null hypothesis. Otherwise, you would reject the null hypothesis. The concept of the null hypothesis is similar to innocent until proven guilty. We assume that the mean salary is $113,000, and we try to prove otherwise. Alright, this was an example of a two-sided or a two-tailed test. You can also form one-sided or one-tailed tests. Say your friend Paul told you that he thinks data scientists earn more than $125,000 per year. You doubt him, so you design a test to see who's right. The null hypothesis of this test would be, the mean data scientist salary is more than $125,000. The alternative will cover everything else. Thus, the mean data scientist salary is less than or equal to $125,000. It is important to note that outcomes of tests refer to the population parameter rather than the sample statistic. As such, the result that we get is for the population. Another crucial consideration is that generally, the researcher is trying to reject the null hypothesis. Think about the null hypothesis as the status quo, and the alternative as the change or innovation that challenges that status quo. In our example, Paul was representing the status quo, which we were challenging.
For more videos.
Okay, so this is the rough idea of hypothesis testing, but some of the information in the video test is very good video, but some is incorrect. So let's check with my lesson. Okay, so yes, typically hypothesis testing, we have 4 steps. Okay, first step we call set the hypothesis. Okay, we have 2 hypotheses, H0, or we can say H naught. H naught. And then we have a pair hypothesis we call H1. Okay, but some textbook they use HA, the same. Any H1 or HA is okay. Second step, we calculate a test statistic. For example, Z statistic or T statistic. Third step, we open the table to find a critical value or a decision rule. Okay, so we would like to know that is 1 tail or 2 tail. Lastly, we make a conclusion. Okay, so we can either do not reject or reject H naught. Okay, so for H naught, we only use reject and not reject. You can say except H1, but we don't say except H naught ever. Do not say except H naught ever. Okay, so let's see step by step. Step 1, state the hypothesis. Okay, so H now is now hypothesis, H1 alternative hypothesis. H now is always presumed to be true. The alternative is paired with a hypothesis. And then the red text is the most important here. Equality is always part of H naught. Okay, so equal, greater or equal, less or equal, always go to H naught, and this is the ultimate rule. Not equal, greater, less than H1. For example, if I would like to test that beta is greater than 2 or not. Okay, we would like to test that, okay, this beta is greater than 2 or not. Then greater, no equal sign, no equal sign. So this must go to H1. Then H0, H1. So H1 beta greater than 2. You have to pair them with red. Red. Very good, very good. One more example. I would like to test that the price equal $30 or not. So equal sign go to H now or H1? H0, yes. So you have to write H0 price equal 30 versus no, price is not equal 30. You have to pair them. Equal pair with unequal. Greater pair with less or equal. Less than pair with greater or equal. Okay. If we conclude, do not reject H now, it does not necessarily mean that the null hypothesis is true. It only suggests that there is not sufficient evidence to reject. However, reject the null hypothesis suggests that the alternative hypothesis may be true. Okay, so to summarize, first step, equality away H naught, the ultimate rule. The rule of significance, we learned it already, so you can read it after that. So second step, calculate t-stat, or it is statistic. So this is the test t-stat. So t calculation t equal the forecast value minus the value you want to test it over standard error. Then third step, you try to find a critical value or a decision rule. A rejection region depends on H1, greater, less than, or unequal, and a level of significance. And step 4, we make a conclusion. Okay, we make a conclusion, reject H now or not reject H now. Okay, we do not say accept. Okay, our decision is incorrect if it's true, but we decide to reject, we call type 1 error. If it's false, but not reject it, we call type 2 error. Okay, this is not that important, just information. Okay, this is 4 step, lastly, but we will do it together. The important step is step 3, how to find a critical value. I said it depends on H1. Then practice together. Okay, so in the third step, I always recommend my student to draw a normal distribution and you will not confuse about your answer. Okay, let's start with the most easiest one. If we test whether beta equal some value versus no, it's not equal. It's not equal, it means it can be greater or can be lesser than C. So this type of test we call to tell. So for to tell, we after we write normal distribution, you can give a t-value on both sides equal t and minus equal 3. And then if your value is on the center, you conclude H naught. But if it's on the left and on the right, you conclude H1. Okay. How about if we would like to test whether beta is greater than some value? So greater than is one tail. Yeah, good. And then one tail, since it's greater is mean is on the right. So you have to find critical value on the right. And if your value is in this area, H naught, H1. Again, less than is one tail on the left, and you have to set minus. Yeah, and here is H naught, H1. Okay, this is like a summarize how to draw a normal distribution. Then all information together, we now can do hypothesis testing. Let's do it together. So this is the data we obtained before, okay, beta 1.93 with standard error. Here is standard error, yeah, 0.26. And then we would like to test whether we can trust this number or not. Okay, so we would like to test, okay, if whether if X does not affect Y, it means, oh, the real value of this beta is 0. If it's 0, X multiplied by 0 equal 0. So, no, the beta. Yes, it means even you make X higher and higher, if the beta is 0, anything multiplied by 0 is 0. It means in the text, you can say that, oh, you mean X does not affect Y. So we write down in equation beta 2 equal 0. Okay, since equal, you have to go to H naught. And then you have to say, oh, equal, you must have the parent HH1. So you say, no, beta 2 is not 0. Or in verbal, you say, oh, X affects Y. Okay, it can affect on the positive way. It can on the negative way, so we can say is to tell. Good. Okay. And furthermore, when you set the hypothesis testing, okay, you would like to test about the two value. So do not put hat on it. Okay, that's why H now beta 2, not beta 2 hat. Beta 2 hat, we know already beta 2 hat that we estimated is 1.93. But we would like to know whether the real value is zero or not zero. Okay. Then step 2, we calculate a test statistic. So this test, you have to use t-test. So t-test equal beta hat. Here, we already have it. Okay, we change the calendar to make it more easier to see. Beta hat already get it. The C is the value you would like to test here. And standard error here. So 1.93 minus 0 over 0.26, and after you get the calculation, you get the number 7.57. Just keep it in mind first, because the third step, you have to find critical value. So to tell 95% is mean 95% on the central, and then this is another 2.5. So you have to open to 0.975, which came from 2.5 plus 95. And the key of freedom is n minus 2. So you get the number t.1a2. And after the third step, you get the critical value t. I recommend you to write down normal distribution. And then put the critical value here, because it's two tail, you have to write on both positive and negative, left and right. Then if this is S out, it is S1. And then bring the second step value to conclude. Okay, this is the critical value, but the second step, the test statistic, we got 7.57, which is exceed critical value, or it will fall down at H1. Then you can make a conclusion. Okay, the second step, we see that is at H1, so we can say we reject H now. Okay, or we can say we accept H1, which means, okay, write, you can copy the word from H1. Okay, after we reject H now, it means, oh, real beta 2 not equal 0, or X affect Y. Okay, I love this phrases. Significantly at confidence 95%. This is called hypothesis testing. So you have to write down this word after you test is significantly, okay, you can say at 95% confident or at 5% significant level, significance level, maybe significance. I don't know how to write it. T or CE. Not sure. I always confuse between two words. Significance or significant. But okay, they are the same thing. Or you can write down at alpha equal 0.05. Okay, so the keyword is significant. Okay, see more example and you will get used to it. This is another example and we have a different data. Okay, y hat equal intercept plus slope xi. So beta 2 equal 7.55. But we don't know that we can believe this number or not 7.55. So we have to do hypothesis testing. Then they would like to test that whether y affect, x affect y positively or not. So we change from verbal x affect y positively to be beta to greater than 0. This means the beta is clear positive. Answer me, one tail or two tail? One tail, good. Then greater, no equal sign, right? So you have to go to H1 and then pair with H naught less or equal 0, or verbally is X does not affect Y or affect negatively. This is the most important that you have to set hypothesis correctly. And there is only one rule: equal sign always in H naught, equal in H naught, equal in H naught, equal in H naught, no. Okay. Most important, if you set hypothesis correctly, you will not confuse about your answer. Then second step is that equal beta minus the number that they concern over standard error. Or it means you can use beta divided by standard error. So 7.55 over 6.26 evidence. 1 point something, 1.06. Thank you. Just keep it first because you have to go third step to find the critical value. Okay, so this is 1 tail is mean greater. This means on the right, and this is 95%. So T 0.95 n minus 2 n 50 28. Good. Very good. 28. Then you have to see the table 95, 28, 95 or 24, maybe 25, and sorry, 95. Okay, I will teach you how to use this table. This table is very convenient because they already have provide you two tail, one tail. Okay, so previously we would like to use one tail 95%, which means 5% error, and degree of freedom 28. So you get good. Wow, you understand this clearly. I'm very proud of you. Because I taught similar thing to my undergrad students. So, what is your number? They keep silent. And, oh, what happened to my lesson? Why they don't understand? What number? Okay, so we now ready to make a conclusion. So you have to draw normal distribution. Greater is on the right. So the third step, 1.701. This will be H now. This will be H1. Then, since your calculation is only 1.206, so this area or this area, yeah, 1.206 is H now, right? So conclusion, we reject or not reject. Do not reject H now. H now or H zero, that's okay too. You can say H zero or H now. Okay. Do not reject H now. So can I say accept H now? Can I write it? No. Don't write this. You cannot write accept H now. You can say only reject or not reject. Okay, so this one, you would like to summarize H now, but you have to say you not reject H now. Okay, and then you can write down the answer. You may write H1. Okay, that we do not reject H now, which means beta to greater than 0 X affect Y positively is not true. Okay, this is the start when we have to conclude S now. So we can write down, oh, S1 is not true. Or you can say X affect Y positively, but okay, it's not true or but not significant. This one is acceptable also. Okay, you can say not true or not significant, which means you use statistical term to explain. Yes, significant. Okay, so one more example. This time we have a negative value, and then n is equal 10,000. So literally means you can use infinity. Okay, so this time they would like to test whether x affect y negatively or beta 2 is clearly less than 0 or not. So we have to pair them with greater or equal. So equal must be in h naught. Second step, equal beta hat minus the number you concern 0 over standard error. So it means you can use this number over this number. So minus 4.55 minus 3 point something. Minus 4.55 minus 0. Yes, yes, minus 4.55 minus 0, but minus 0 is meaningless, right? So we have only minus 4.55 over to 1.26. Yes, you can write it. No problem. And what the number you get? Minus 3.61. Thank you. And third step, find the critical value. So you have to open t 0.95 infinity. And you get one tail, sorry, one tail. One tail. And yes, you can go to yes, 1.645. Okay, good. Good. 1.645. Then you draw normal distribution less than other less than h1 is less than, so you have to make critical value other left or right, left with the negative value. So this is minus 1.645 h now h1, and your second step, your calculation is minus 3.61. Which area? Left or right? Left, right? Very minus 3 point something around here, minus 3.61. So go to h 0 or h1, h h1. Yes, so we reject or not reject h naught. Reject, yes, correct. Reject because we go to h1. we say, oh, S now is not correct. We reject H now. What does it mean? It means beta 2, you can write down this word, okay? Beta 2 less than 0 or X affect Y negatively. And please write this word as well, significantly. Significantly. And 95% confident. Or 5% significant level. I don't know the maybe 95% confident, not level. Okay. And 5% significant level or alpha equals 0 level 5. You can write any of those words. Do not write them all, just one of them. Okay. But this is like an example how to write the result. For example, when you have to write your report, you may find very boring if you write down only the same word, 95%, 95, 95. You may change the words from time to time. Okay. To make you more understanding, better if I would like to test, okay, I would like to know, okay, this is minus 455. Can I conclude that the real beta equal minus 4 or not? Okay, so you have to set the hypothesis. So H naught, H0, that's okay. H naught, this one go to H0 or H1, equal sign, H naught. So beta 2 minus 4 versus no, is not. Yeah, so this is your 2 year. Very good, very good. And then second step, you have to calculate t. So t equal this one minus 455, and the number that you interest so is minus 4. So minus 4 over 1.26, and you get the number 0.55, right, over 1.26 using your calculator. 544. So thank you. Then third step, you open the table and you will get, yes, you know it already. The one that you remember, two tail. Good. Yes, 1.96. Okay, this is like a magic number. We use it frequently. Then after you obtain all the information, you draw the normal distribution. And two tail, right? Minus. Then your second step, 0 point something, right? So around here, which means you go to H. No. Then you conclude that you accept H now? No, you have to not reject H now, which means we can conclude that beta 2 not equal 4. Oh, sorry. Not reject, right? Not reject. We can conclude that beta 2 equal minus 4. Okay, that's how we do hypothesis testing. And then you may talk to me like, hey, professor, when I have to work with your data, do I have to do those complicated tests? The answer is no, because the software already help you. The software will provide you p-value. Okay, this is the printout of program. Okay, and you have to know how to read them properly. So first, this is dependent variable y. C is constant, which means intercept. X is explanatory variable. So this is coefficient. This means this equation means y hat equal constant here 0.33 plus coefficient here 1.93x. Okay, and then this is standard error. Okay, this is beta. So the standard error, when you have to write the equation, you have to put in the bracket under is beta here 0.25. And then this is the t-stat that they set h now beta equal 0. So from the t-test t equal beta hat minus 0 because they set to 0 over standard error. So beta hat over standard error. What does it mean? It means if this is 1, this is 2, and this is 1 over 2. Okay, and it will be in the exam. In the exam, in the exam, I may hide some value here. For example, I may hide this value. I may hide this value. Then you have to know how to calculate it back by, okay, t stat is maybe number 3. So 3 equal 1 over 2. Then you would like to find 2, right? So you can choose that 2 equal 1 over 3. So you use this t stat, you use this coefficients, you can calculate back standard error. Moreover, included observation, this is n equal 5. And t stat here, normally the t stat here, since they always love to use 95%. And the magic number, what is the number again? 1.96. Okay, so if you see the t-stat and is greater than 1.96, it means it's go to H1. It's called significant. So there's a way see that, okay, if t-stat is greater than 2, it means those beta significant or is affect Y significantly. Ah, this is the real meaning. Oh, and you may say, Professor, that's still inconvenient. Why I have to see whether it's greater than 2 or not? How about if n is not high enough? So then I'll provide you also the probability. And this is the main thing that the researcher see your model, I see the model. So this is the probability to go to H0. Let's see the relationship. So if this probability is less than 0.1, it means it's significant at 90% confidence. Significant. Oh, my English. Significant. Significant. Okay, at 90%. So probability here is the prop to go to H now. So if it's less than 0.1, it means 90%. If it's less than 0.05, it means 95%. If it's less than 0.01, it means 99%. So can you see the relationship between probability and the level of confidence? Okay. So after you get this output, okay, you can see the probability. Okay, for example, the beta 2 here, and you can say, oh, it's zero since plot t. I would like to write in the full sentence. So beta 2 hat equal 1.93 with of t equal 0.0048, which case 0.1, 0.05 or 0.01, 0 to 0 here. So this case, so you can say, oh, is sorry for my mistake. Please write equal. So e less than equal 0.01, which means significant. Good. So which means if x increase by 1, y will increase 1.93 significantly. Oh, my English again. I will write too quick and make a mistake. So significantly at 99% confident. Okay, so in real world, when you tackle with the real data, we can just see the probability and then we can conclude. We do not have to open the table over and over, but you have know how to obtain the data, right? How to do the hypothesis testing. I think I already provide you a homework as well, so you can practice how to do the hypothesis testing. Okay, so next week I will give you a homework solution. So make sure that you try it first, and then we will work together again next week before we start the next chapter. So make sure that you do it correctly. So this is the homework. Okay, I provide you 3 homework, but have a lot of stuff homework. Homework 2.1, okay, they have A, B, C, D, E, okay. It's 3 homework, 2.1, 2.2, and 2.3, but have a lot of A, B, C, D, nah? So it's like you have 10 homework, not 3, okay. Okay, so simple linear regression, 24 observations, log is 0.31. Standard error is 0.082. A, there's a hypothesis low, 0. Again, it is not. Okay, so let's try. Second, let's try slope is positive. Okay, so let's try beta is positive. This is beta not 0. This is beta negative. And then let's try equator beta is 0.5. And then please do a confidence interval. So just check your understanding of hypothesis testing. Okay. Second homework is very long, so let's slowly read the question. So MIM is mean income of male, okay, in thousands of dollars. While PMSH is the percent of males who are high school graduates. The data consists of 51, so NEO 51. And this is their equation. Okay, so they try to hide A and B. So this is standard error, and this is T stat. So 1, 2, 3 equal 1/2. So A, please find intercept or A. B, please find B. Okay, so you can do it using this equation. 3, state the economic interpretation of slope. Okay, so you can write down how about the relationship between this is like a year of schooling, right? The percent of male in those states. This means the effect of school to income. So let's try to explain what is the economic theory. Then D, please construct 99% confidence interval. And lastly, please test whether beta equal to. Let's try first because next week I will give you a homework solution. No problem. Try it first. Next week, do it together in the class again. And 2.3. So this is like a computer exercise. So after we finish today, I will teach you how to use the program. Okay. So the data of 1,000 observation on wage, hourly wage, depends on experience. So the higher experience, the higher wage or not. So they plot the scattered diagram here. And this is the result. Okay, so using the program to reproduce both the plot and result. And then please also interpret the result can be summarized that experience affect wage rates significantly. Okay, so I expect you to do two things. First, try to use program to make this output. And second, interpret the result. Okay, so in the classroom, Google Classroom, I provide you the data already. Okay, this is in the Google Classroom. So this is eView file and this is Excel file. Do you want to try first or move to next week and we do it together in the class right now? Let's go. Why not? Oh, sorry. Okay, so download the data first. CP S4 small Excel. Okay, this is the data. This is the data in Excel, and this is the proper way when you have to collect the data. You have to have the variable name on the top row, like this, and the rest is the data entry. For example, the first person, they get the weight 1.97 with the experience 51, which means 51 month, I think. 51 month. Okay, so this is the data that we would like to estimate. We would like to estimate the relationship of the color is bad. We would like to estimate the relationship between wage and experience. So we will use two variables together. Okay. So after we obtain the data similar to this, how can we use this data in program? So you have to install eView. I think they already provide eView in your laptop already. Yeah, please open eView. Okay, open eView. So it means homework 2.3 I will teach you to do in the class. So you just do the second one to interpret the result. Okay. Okay. So it's easily if you already have a review, but if you don't have how to deal with that, so imagine that you collect the data for your research in Excel, then you would like to import them to Evo. How? How to do that? So in the Evo, click File, Open, Lens Data as Word file. Okay, on the top left, open Lens Data as Word file. And choose your Excel file. Just leave it there. Don't check. And if you do it correctly, you can click finish. You can click finish. And if they ask that you want to like thing, please answer no. It's better no. That's all. Very easy, right? Yes. Because previously you open eView. This is the new data that you import from Excel. Okay, click no. Okay, open foreign data work file, choose your Excel file, then finish. If you did it correctly, it's automatically in your review. Easy, right? Then we would like to plot the data first. So we plot wage with experience. To plot the data, you have to click on the data. So let's click expert first. Expert with me, experience. And then use the control button on the bottom left of your keyboard. Control and click on which either. You have to select two data together, so you have to use control here and click which. Yes, good. Okay, expert control and click which. Okay. In your download. Let's go to download. Okay, good. Okay. Let me read the error. Download. No. Here, come on. Left. Excel. Okay, you have to close the Excel first. Okay. But that's okay. You can use this one because they are the same. Okay, so click on expert, EXPER. Now, yeah, and slowly close. Okay, and then use control. Okay, and click on which. You have to click on control also. Okay, back to step expert first. Expert control. Click which. Good. Okay, you have to select two data together because we want to plot the figure. So right click, use your mouse, right click, open as group, right click, open as group. Yeah, open as group. And then the data will pop up in the new window. Okay, so we have two variables now, experience and wage. Then we would like to plot the figure. So click on view graph. Okay, view graph. Yes, and try to see scatter. Yes, and then choose which line to be the regression line. Second one. Good. Okay. So scatter. Yes, scatter and which line. This should be regression. Yes, the second one. Yes. Okay. Good. Yeah, sure. This class will be this lecture already, so I will post the video. So to make sure that you can review the lesson repeatedly. Okay, so class, scatter, and regression line, and let's see the result. Click OK. Okay, so this is what they expect you to plot. You can see the relationship between experience and waste by using scatter plot. And okay, this is your regression line. It's not so good if you can see it, right? Because your data is very random and you try to estimate using this line. But okay, for this class, just to practice, we will try to estimate this line using EView. And we will finish. Okay, so to make the OLED lines in EView, let's back to the main work file where all available here. And then click on object and new object. Object, new object. And then the first one is equation. So please name equation here. For example, equation O1, EQ01. Yeah. Equation, name it. Equation 01, EQ01. Okay, EQ01. And then you can write down two ways. First way is to write the equation in full, inconvenient, but you can write in detail. I will teach you. So the equation that my homework would like to do is, okay, I will write down. I would like you to use Wey's equation equal beta 1 plus beta 2 experience. So in EView, you can write down wage equal, instead of beta 1, in EView they use C1 plus C2 x per. Let's try this one together. So in this equation estimation, make sure that your method is least square OLS. And then type which equal C1 plus C2 star X per. Yeah. Yes, yes. Start. And then click OK. Yeah. So that's all. When the work is not difficult, like if you know how to click, they just, oh, a lot of mathematics, minimize error, a lot of things. But program can do it for you, but you have to know what is inside. Okay, so this is the first way, and the more convenient way is you can type wedge spacebar constant x per. You can just type like this, and this is more convenient. I prefer this method. Yes, so let's click on I delete them all. Okay. Oh, sorry, accident. So let's try this one also. Waste the x per. Okay. So you may repeat the step: object, new object, equation 2. Yeah. And then try this method as well. Waste the x per. It means expert, XPR, yes. This this can be both. They, they can be small or yes, you can do because in EView, this program, this means they are not case sensitive. This means you can use the bigger alphabet or the small alphabet. It's the same on EView, but not in Stata. You may later learn Stata. Cannot. Yeah. EView, that's okay. For EView, that's okay. Okay, so this is how we estimate equation on EView. Okay, so it means when you write down, it means you would like to estimate where equation depends on constant term, intercept, and experience. So your homework here is please interpret this probability and how experience affect on wage. Okay, write it first. I will give you a solution next week. Okay. So this is your first step in review. I will teach you further, of course. So let's go to practice how to read the probability, which very important concept of this subject. And then see you tomorrow. Not tomorrow. Next week is better. Tomorrow you will, my head bang. Okay. See you next week. ขอบคุณครับ